When we talk about static scoping, so the question that we have to ask ourselves is, how do we find during runtime the correct location of the actual variable that is in the parent of in the static parent of the actual current scope we're in. Now notice the dilemma here. We have to decide during runtime where on the stack is that variable that we are actually trying to access, and taking into account that there could be a very big distance between the current frame on the stack and where that frame is. And why is that true? Let's think for a second about a picture that looks something like this. We have a runtime stack, and we had a function main, right? We had the function main that called some function x, okay? That called itself, let's say, recursively 25 times, okay? So this is x1, and this is in a sense x25, right? And we have a whole bunch of other x's here in the middle. And that called the function z, right? That was our picture from before, okay? So now in x, we had the variables in x. Just to recap, we had the variables a and d, and in main we had a and b. So every one of these x's has an a and a d. And main has an a and a b. And we are currently in the scope up here, where we had this little piece of code that said C out a plus b, right? So now we need to ask ourselves, which a, which b? And more importantly than that, where is a and where is b? Now, the compiler cannot know in advance what the distance between the place where you actually call or use the variable and its location. Notice that this number 25 here that we had here, these 25 iterations of x that we had right there, right? All these 25 iterations, the compiler didn't know about it. It's some recursive function. It has no idea how many iterations it will go through. It's something that only during runtime we will get to see. So how do we find this guy? That's our target B, right? That's the question we have to ask ourselves. And also, out of all 25 A's, which is the A that we're talking about? There's 25 different A's here. So we have to figure out, how do we go about doing this thing, okay? Now, our assumption here is going to be that we're going to do this in 2 steps, and we're going to make an assumption. The 2 steps are, in a sense, finding the correct frame and then finding the offset within the frame. We are going to assume, though, that it is on the stack somewhere. Because if we look again at our previous picture from right here, in order to be within the scope Z, you have had to be within the scope X, which had to be within the scope main, because otherwise it wouldn't be accessible. For example, the scope Y cannot call Z, right? Z is a scope within X. So Y cannot actually access Z. So if I am now within Z and trying to do this C out A plus B, I am going to make an assumption, which is a valid assumption, that X is on the stack and main is on the stack. I don't know where, right? I do not know where. It could very well be that I even have a Y here in the middle somewhere, right? Let's change the picture a bit and add here Y, just for the sake of the completeness, right? So let's say this was Y that called X, and this was main, right? This was main. Here we had an A and a B. And we are actually talking about this B that we're looking for. So I don't even know, how far down and how many other scopes actually, came into the stack here, to the runtime stack here somewhere. So the question is, how do I find this variable B? And as I said, we're going to make an assumption that it is somewhere on the runtime stack. So the first step in doing this is that the runtime stack on the frame is added what's called a static link. A static link means that we are connecting, we're going to go and we're going to connect the frame with its static parent. Meaning to say, for example, the static parent of Z is X. The static parent of X is main. The static parent of this X is also main. And the static parent of Y is also main, right? They're all main, right? They're all connected to main. So in a sense, the idea is that I'm going to go and I am going to connect to main. Here we go, to main, right? Not to Y. I am going to connect all frames to their static parent using what's known as a static link. Now, when I look at all the static links together as a group, in a sense, what I get is a static chain. Notice that we have a chain here. 1, 2, right? This is a chain. So if I go and I follow through on our links, we actually get a static chain. Now, the question is going to become, how do we do this? And I'll talk about that in a second. But let's assume for a second, that we have a static link connecting every scope to its static parent. So now searching for B becomes a lot simpler, because now I jump over the 25 x's and it's all meaningless, right? I can jump over Y. Notice I'm skipping over Y because Y is meaningless. As far as Z is concerned, Y is not there. So if I can actually arrange for all these static links, then I can actually solve the problem very simply. Now, the way this is done is the following. Before talking about how we know where the static father is on the runtime stack, before we do that, let us ask ourselves, so assuming we do have a static chain and static links and all of that, how do we find the actual variable B that we're looking for? Now you can say, okay, start following the chain, and as you go through the chain, search every one of those frames. But that's a bit meaningless. Why is that meaningless? Because we don't have variable names anywhere, right? So how do I know? Right? Anybody who did the lab number 2 would know, or even lab number 5 already, would know that there is no variable names once we get down to the runtime, right? To the code that runs. So how do we actually know where the variable is? So we can search for it, but that wouldn't work too well. So the answer to that is very simple. The compiler during compile time goes, and for every scope, it gives what's known as a nesting value. What does a nesting value mean? If we assume for a second that the nesting value of our main is 1, so the nesting value of X will be 2. It's nested one more level in. The nested value for Y is 2 also, and the nested value for Z is 3, right? It's nested one more value in. Okay, so now the compiler can go and say, okay, if you want to know how many links you have to surpass on the chain to find your static father, right? So the answer to that is that we check what is the difference between the nesting of the calling function and the nesting of the scope, not function, of the scope where the variable has been defined. So for example, in our case right here, the calling of the function is nested at 3, and the variable has been defined at 1. So 3 minus 1 is 2, and that tells us that we need to go and we need to traverse 2 links on the static chain to find the static parent. So if we look at our static chain that we have over here, and we say, okay, we have 1, 2. So we traverse 2 links on the static chain, starting at the current frame, and we get 1, 2, and we arrived at main. Okay, so by subtracting the difference of nesting between the calling and the declaring scopes, we're actually being told in advance how deep we need to traverse on the static chain to find the frame where that variable exists. Now, the second part of this is very simple. Once I know the frame, once I know where the frame is, so the compiler is the one who actually built the way the frame looks, what's known as the activation record instance. Activation record instance, that's the name, okay? And the compiler knows what the instance looks like. It means it knows, for example, the variable b is an offset k, whatever k happens to be. So all the compiler has to tell you when you want to access b up here, all the compiler has to tell you is the following. It wants you to traverse 2 levels on the chain and go indent k offset. And when you're told that, you actually found the variable b in a sense without searching for it. You're just told where it is. So if we go back and we ask ourselves, which a of the 25 x's that we have here is the a that we're going to use? The answer to that is it depends on where the static link is pointing. Does the static link point to the x25 or does the static link point to x1? The answer to that is it depends how we build the static link. And we're going to the algorithm how to build the static link, so we'll know how to answer that question. But if the static link actually points, the static parent of z is x25, then we obviously use the a at x25 because the variable a is actually at one move on the chain, because we have, in a sense, when we look at the scoping that we have here, so the variable a is at 3 minus 2, which gives us 1, and therefore we move one link on the chain and an offset m, whatever it is, in the picture that I have drawn on the right. So it might be at there's a, it might be at offset 5 or 6, or whatever the offset from between here, whatever the offset between here and here is, if we assume that that's the base, or the offset from here to here, if we assume that EPP is the base, whatever your base, wherever you start your base, the compiler already knows where the A is as compared to that point. And therefore, whatever that is, we'll call it M, right? So the compiler will tell you to traverse one link on the chain and go at offset M. So the question is this chain, the link taking me to x25, or is the link taking me to x1? That's really the question. And the answer to that is it's a function of how we actually build this static, the static link. So how do we actually do that? How do we actually build the static link? And the answer is actually not difficult at all. When, again, we're going to use the help of the compiler. And we're going to say to ourselves, the compiler is going to look at this picture, and it's going to say to itself, what is the difference between the place where the variable is being used, let's call that the calling function, the calling scope where it's being used, and the scope of the parent of the function doing the calling. What that means is the following. Let's look at our calling chain, and we have this main calling y, calling x, calling z. Okay, we have x calling. Now let's draw a picture again, and we have over here, we have the main. This is our main, which called y, which called, let's say x 25 times. We said that already. So let's make that a big, x1. This is x1, and then we have whatever. And then we have 25x25. And now we are calling z, right? Now we want to call z. Now let's draw a picture, for example, of how the chain looks right now. So right now, y is pointing at main, and so are all the x's. They're all pointing at main. Because if we look at our picture from here, then we see that they are both the static parent of x and y is main. Now we are going and we're looking at z. And we ask ourselves, what is the difference what is the difference between the nesting of the calling function, which is x, and the nesting of the parent of the called function, which is also x, right? We are having x is calling z. And we ask ourselves, what is the difference between the nesting of the calling function, which is actually 2, and the parent of the called function, which is also 2, and the answer to that is 0. So when we go and say who is the parent, static parent of z, the answer is traverse 0 links on the static chain. That is your parent. And therefore the parent of z is x. Actually x25. Let's look at the other example that we had before, that we had main called x, which called z, which called y. Okay, which called y. So we would draw that the following way. On our runtime stack, we had main, which called, again, we'll do 25 x's just for the completeness sake, which called z, which is now about to call y. Okay, now let's draw the links right now. So we said that z is pointing at x25, and all the x's are pointing at main, right? All the x's are pointing at main. And now we're about to call y. So we ask ourselves, what is the difference between the scope of the calling function, which is z is the calling function, and therefore the scope, the nested scope of the calling function was 3, the nested value was 3, minus the parent of the called function. Now, if we go back to our picture, so the calling function was z, which is its nesting value was 3, and the parent of the called function was, well, the called function was y, and its parent was main, so it has a value of 1. So we actually get 3 minus 1, and we get the value 2. What that means is traverse on the static chain, starting at z, who's the one who's calling you, 2 links, and that is your static parent. So when we go and we create z on the y on the stack, so we would say, okay, let's traverse 2 links on the static chain. So therefore we have 1, 2. That is your static parent, and therefore you will make the connection like that. Now notice that we were able to find the static parent of y on the runtime stack, regardless of how many x's we had here, or how many other things that we had, like this thing. We can z can be recursive as well. It doesn't really make a difference. As long as we actually uphold and we follow through on the algorithm for building these links, then the chains will do all the work. Okay, so we're actually doing now everything now in 2 levels, in two stages. Stage number 1 is every time during the calling protocol of a function, the compiler sticks in a code of figuring out where the static parent is on the runtime stack. And the way it does that is the compiler decides what is the difference between the nesting value of the calling function and the parent of the nesting value of the called function. And that's how many links you have to traverse on the chain in order to find the new static parent. Now, once we have the links, when you access a variable, the compiler does the same thing. The compiler says, okay, how many links do I have to traverse on the static chain in order to find the correct static frame? And then what is the offset within that frame? So notice that everything is actually being done at compile time. All the hard work, in a sense, all the mathematics, which is not so difficult, right? It's just subtraction, is actually being done during compile time, because we are talking about a static picture. But the code that actually gets the work done is actually done during runtime. Okay, so that's how static chaining is actually accomplished. And let's talk about the downsides of static scoping. So the first downside actually of the static scoping is the fact that accessing variables is not a constant function, meaning notice that the variables A and variable B took different amounts of time to access. Variable A needed one move on the chain, and variable B needed two moves on the chain. Now, that was a simple example with 1 and 2, but it could be that one variable is K links down the chain, and another variable is M links down the chain, and accessing the different variables is not a constant time function. Now, you would say, who cares? The answer to that is that when we want to evaluate the runtime of programs, we can't go and say, oh, this variable takes that amount of time, this variable takes that amount of time. We want to access things in constant time. And therefore, this is actually a detriment. This is actually one of the reasons that C-based languages do not do static scoping. They do not allow for static scoping. They do not allow for any scoping at all, as a matter of fact. They only allow for, should we say, block scoping, and we'll explain in a minute why that's different. But in a sense, they don't allow scoping because of this lack of constant time value. Now, the second downside of this static scoping is that the structure of the code influences the amount of time that you can access that variable. It means if I change the structure of the code, then the time for a specific variable changes. Because it could very well be that if I do some kind of refactoring or whatever I do, and suddenly I get a whole bunch of subscopes and subscopes, suddenly some variable which used to be, let's say, 1 scope away is now 5 scopes away. So the amount of time that it takes me to access that it changes. Now this link between the structure of the code and the access time is something which is actually detrimental to real-time systems. You don't want to actually have a real-time system and you sit down and you rearrange the code. I notice I didn't say change the code. I'm talking about the structure of the code, and suddenly everything changes. That doesn't make sense. And therefore, these are actually detrimental to runtime systems, real-time systems.